When the iconic Netflix show Squid Game came out, fans all over the world were fascinated by the Dalgona candy featured in one of the challenges. Many have tried their hand at making it, and while it is a delicious treat, how is it actually formed? Dalgona candy is formed using two processes. First is caramelization, which is the oxidation of sugar. The process involves heating sugar so that sucrose molecules are broken down into glucose and fructose, and removing water as steam. Volatile chemicals are released, thus producing the characteristic brown color and nutty caramel flavor. Caramelization temperatures range from 110 to 180, and despite popular belief, it is a quite complicated process. The three processes of caramelization are as follows. First is enolization. Often, caramelization starts by reordering within the sugars themselves through enolization. A sugar molecule with a double bond between oxygen and carbon now becomes a molecule connected to one carbon and one hydrogen atom. So, the reaction is when a sugar molecule in keto form changes to its enol form. Second is dehydration. Individual sugar molecules lose water molecules through a reaction called dehydration. And there are multiple ways that this can happen, but at the end of the day, when you do this experiment, you will see steam. Lastly is color formation and flavor formation. Polymerization gives caramel its unique color. The large molecules are formed through oligomerization. Three common molecules that form are caramelin, caramelin, and caramelin. Fragmentation produces the caramel flavor. The smaller aromatic molecules can actually evaporate and reach your nose. Commonly formed molecules are diacetyl for a buttery flavor, esters and lactones which have a sweet rum-like flavor, furans which have a nutty flavor, and maltol for a toasty flavor. Now, there are three factors that affect caramelization. First is the temperature, second is the type of sugar, and lastly is the pH value of the solution. This can cause the reaction to speed up or start at a lower temperature. The second reaction in Dalgona candy is leavening, which is the decomposition of baking soda. In baking, it causes the expansion of dough and batters by the release of CO2. The carbon dioxide produced during its decomposition makes the Dalgona candy puff up. Baking soda is a base, NaHCO3. It reacts with an acid in an acid-base reaction, producing water and carbon dioxide. Once these gases are formed, the reaction cannot go backwards again as easily. Thus, they will evaporate away. Now for the experiment. The standard recipe I used is shown here on the screen. In this experiment, we will observe the effect of baking soda on the candy. As the sugar heats, you can clearly see the color change due to polymerization. And when baking soda is added, the mixture thickens and turns opaque due to the carbon dioxide produced due to leavening. This is our control experiment. For this batch, we'll halve the amount of baking soda. As you can see, the mixture is not as opaque and it is still quite liquidy. For this batch, we'll use double the amount of baking soda. This mixture is much thicker and lighter than the previous two and is the most opaque out of the three. And here are the results. Bigger amounts of baking soda mean bigger amounts of carbon dioxide, but also bigger pores on the surface of the candy. As a result, a decrease in baking soda means less carbon dioxide, resulting in a denser candy. An increase means larger air pockets, resulting in a more brittle candy. In terms of color, it's evident that the longer you cook the sugar, the darker the color will be. However, we know that the pH level of the environment affects caramelization as well. The rate of caramelization is generally lowest at the pH 7 and higher under both acidic and basic conditions. Baking soda is a weak acid, thus it increases the pH of the sugar. As a result, it speeds up caramelization, which is why the candy with the most baking soda had a darker internal color.